a great pleasure to introduce today's speaker, Maya Cakmak. Maya received her PhD in robotics from Georgia Tech, where she worked with Andrea Tomas. She's currently a post-doctoral research fellow at Willow Garage, which is the most influential robotics research lab in the world. It's still in existence. And Maya is working on human-robot interaction, which means she doesn't just worry about getting robots to navigate from one place to the other or to build maps of environments or have quadrotors flying around, but she really looks at kind of the next generation of robots that have to collaborate with people to solve certain tasks. And today she's going to give us an overview of her work in teaching robots by demonstration.
Thank you. That's a good primer. So yes, a lot of my work is in human-robot interaction, and this is a growing area in robotics that basically studies the interaction between humans and robots and tries to systematically come up with interfaces and interactions that will support this, the use of robots in context. So the main goal here is to make the interaction more effective and more intuitive for people. And HRI covers a very large range of interactions, from the person commanding the robot to do something for them, to the person working together with a robot to accomplish a certain task. The particular type of interaction that I'm interested in is where the human programs the robot. So where, as a result of the interaction, the person gives new capabilities or new functionalities to the robot. And as emphasized by the title of my talk, rather than robots that are designed for a specific purpose, like the Roomba, I'm interested in robots like this one. This is the PR2 robot, which is the platform that's been developed at Willow Garage, where I'm doing my postdoc. So PR2 is a mobile manipulator, so it can move around, and it has two arms to interact with the environment. And there is a whole lot of useful things you can do by just moving around and interacting with objects, manipulating objects. And indeed, over the 5 years of its existence, the robot has come to have a set of autonomous functionalities, but the robot needs to be programmed to be able to do all these things. And currently, this is how PR2 is programmed. So a group of highly qualified people write C++ or Python code, and they test things on the robot, and they go back and forth, tune parameters, etc. And this is basically the process through which these functionalities are added to the robot. My vision is to enable everyday people who do not necessarily know how to write code or compute inverse kinematics to be able to do the same thing. And one way to do this is programming by demonstration. So here's an example from a recent study that we did, where we allowed the person to demonstrate something to the robot by just moving the robot's arms around and talking to the robot through a very simple dialogue system. Why is it important that we enable end users to be able to program their robots? And why not just have engineers like fully program a robot before it's deployed? So the first reason is that this is very challenging. It's very challenging to pre-program a robot that will robustly work in all the possible environments that this robot might need to operate in. And secondly, we cannot really predict every possible use case for these robots. So by giving this ability to the users, we can really increase the types of applications that these robots might have that we might not think ahead of time. And thirdly, we don't really know how people like things done. So people can be particular about their preferences, and they might want things done in a certain way for reasons that the robot is not able to perceive. So letting them program the robot themselves takes care of this. And people are surprisingly creative about finding ways to do things. So here's an example, again, from the same study, where we see people doing the same thing in many different ways. Now, the applications for such programmable robots, general purpose programmable robots, is virtually anything. Basically, this is by the definition of general purpose. It can be used for any particular purpose within its capacity. So Of course, there's more value to having a robot that can be programmed if the domain has variables, a lot of variation in the different environments, and also there's importance in being able to get information from the user about what the robot will need to do. The reason I put these three applications is that just last week, the National Robotics Initiative announced their newest roadmap for US robotics, and these were the areas that they emphasize as what they want to see the US make impact. And these are actually perfect examples of applications where you could have programmable robots. Why is this challenging? So we actually have a great set of technical tools. So there's 20 years of research and learning from demonstration and programming by demonstration. And the problem, again, is that only experts know how to use these tools. So when we look at these papers in the literature, they're usually evaluated by data provided by the person who built that system. So even some of the very basic assumptions that they make, or they don't even know that they make, can be broken when you have an actual person who's interacting with these systems. So for example, methods that encode movement of the robot's manipulators require smooth and consistent demonstrations of the thing that you're trying to teach. Whereas people are not very good at this. So this is Simon the robot. This is the robot that I used during my PhD at Georgia Tech. And here's an example from an experiment where we have the person demonstrate how to close the box. And as you can see here, the person is moving the arm joint by joint, one joint at a time. And this is not like, even I still do this when I'm teaching the robot, you'll see in the future videos. So then when you learn something from this kind of data, it's really not what you want the robot doing. In addition, our tools assume that people are willing to demonstrate something multiple times, like not even very large numbers, 10 times or 20 times. But people, even when you ask them to demonstrate something 2 times, they're asking themselves, why am I repeating this? Even 5 times is a lot. In addition, our tools assume that if you get the person to demonstrate something 5 times, that will cover the space of different ways of doing it so that you learn a generalizable task. Whereas people, when you ask them to do something 5 times, they'll just do exactly the same thing, and they won't cover the variance that's needed for the robot. So, and basically the reasons for these issues can be traced back to 2 important reasons. So humans, first of all, don't have a good understanding of the robot's inner workings. So they don't understand how the robots represent motion, or they don't really know the limits of the robot. And their mental model, for many reasons, is flawed about how the robot learns. And secondly, people have limitations, like they don't have too much time to spend on the robot. They have limited memory. They won't remember what they showed 5 minutes ago. So a lot of my work basically is about identifying these issues and trying to find ways to address these issues. Now, the key objective in this context of learning from end users is basically to obtain more useful information from people as efficiently as possible. And my work involves a lot of empirical HRI studies, putting people in front of robots and observing. But also it requires a lot of involvement at all levels of system building, from understanding what are the core algorithms that the robot is using for different functionalities to even developing some new versions of these. And also designing every little detail about the interaction. So everything that the robot does in front of the person is going to impact, or might impact, what the person, what input you would get from the person. So what I try to do in my work is leverage all channels of interaction to guide the user towards providing more useful information to the robot. So the work that I'm going to focus on in today's talk is about making robots ask questions to their users during a learning-teaching interaction. And the key thing here is to leverage the embodiment of the robot. And the idea for letting the robot ask questions is that the learner knows what it doesn't know better than a teacher who doesn't really understand how the robot learns. So here's a rough outline of my talk. Basically, I will mostly talk about how can we make robots ask questions to their users effectively. But I'll also talk about some of the other related issues, and then talk a little bit about my future plans at the end. Now, this question, this concept of question asking, queries, is taken from a field of machine learning that's called active learning. And some of you might be familiar with this, but just to put you in context, here's what the core idea of active learning is. So let's say you have these points in 2D, and you have these labels, and you're trying to learn a line that separates the two categories. So at this point, you might have multiple hypotheses of what that line could be, and only points within a certain region will let you make progress towards what the right line is, right? Now, as a passive learner, you could still be getting examples from outside this region and waste time. So that would depend on your teacher. What you do as an active learner is you make queries. So you request labels for specific examples that you know or you have some confidence that will let you make progress. And this has been shown in many applications that it leads to much faster convergence. And there are some theoretical results also. But the core idea is basically to give control to the learner about the data that it receives from the teacher. Now, given this nice property of it converging much faster, naturally the idea has attracted attention among roboticists. So there are a lot of learning problems in robotics. And these problems are quite different. So in many cases, the questions are being asked to the environment, not necessarily a human teacher. But this very simple idea that I just explained can actually be applied in a human-robot interaction scenario when the robot is learning a policy with discrete actions. So when it's learning what to do in a certain state, when you can represent the robot's capabilities in this way. So in this context, then making a query would basically be the robot going to a certain state and then saying, what do I do now? And then the answer is pointing the robot to the right label for this. But discrete actions are quite limiting. So it would be very difficult to come up with a set of discrete actions that you can do manipulation skills like these. Usually what we try to do with these is to represent the motion of the robot with some continuous actions. So what we would do is represent the state of the robot with typically with the end effector of the robot, where the 6-dimensional pose of the robot's end effector relative to some goal, so that if the goal moves around, it's still applicable. And then, since we want to encode the motions of the end effector, the actions would be in a given state, where do you move? So it's these little motions towards any direction. And then by chaining these, you can obtain some smooth movements. Now, again, in this context, if the robot was to make a query, it would be basically requesting these little motions, right? So this is not, people don't really encode movements, especially from the robot's perspective, at this scale. So this turned out to be like a non-feasible path. And it led us to the question of, how do humans ask questions when they're similarly learning skills from one another, or tasks? So we thought that having the robot, basically the idea here is having the robot ask questions in the way that humans ask questions one another would make it easy for people to answer those questions when that question is posed by the robot, right? So we looked in the literature, and there's a great set of work on how humans ask questions when they read a text or when they're learning physics, but we didn't really find anything that informed our problem. So we decided to do our own study on how humans ask questions. So we made up some abstract tasks and skills. These were, for instance, like abstracted scoop and pour would be going to one, turning it one way, maintaining the same rotation, turning it the other way, kind of. And then these would be the tasks that we're teaching people. So we would we would give demonstrations of these tasks to people through video, so they would watch those videos, and then we would tell them that now they can ask as many questions as they want, and then at the end they will be asked to do the task, and there's a reward if they do well on the task. And what we do is we record all of their questions, and we code them in several dimensions that we're interested in applying to robots. Now, the first thing we looked at was the different types of questions that people were asking. So we found that people actually rarely requested demonstrations, which was previously the only way we had thought about making the robot ask questions, right? Instead, more of the time, what people did was do something themselves and then ask if that's okay, if that's that's acceptable for the given task or skill. And the majority of people's questions were what we called feature queries. These were direct questions about certain properties of the task. And we saw several subtypes of these, so we just clumped them together. The first is what we called a relevance query. So if something was varied across the demonstrations that people saw, they would ask whether it matters at all. They would ask whether they can just vary that indefinitely. So here's an example.
And does it matter which way I rotate?
Yes. Okay, and on the contrary, if something was not varied across the demonstrations, people would question whether that has to be an invariant, that has to be that, or whether it just happened to be that in the demonstrations. So that's what we call an invariance test.
Do I have to hold my wrist the same way as I go to the...
Yes.
Okay.
Okay. Similarly, for label queries, we saw these two types of queries. More of the time, instead of making the whole task from 1 to n and asking whether that's okay, people would segment the task into steps and ask, as they do the task, they would do some part, ask whether they're doing okay, and then keep going as they receive the label back from the person. So here's an example of that. So the person is constantly looking at the teacher and waiting for the teacher to nod and proceed to the next one after getting that label. We looked at the question forms and we had everything across the board. But the thing I want to point out is that 85% of people's questions were closed form questions, even though this was not something that we imposed. This means that when you ask the question, there's only a finite set of answers that you're presenting the person. It's either a yes/no question or you're giving them the options. And this was sort of a good news for robots, considering how difficult it is to process an open-ended answer coming from a person. And the most important part that we were interested in, how are people using their embodiment as they're asking questions. So we observed several ways in which humans use their embodiments. First was people interacted with the objects or interacted with their environments to either instantiate feature values or to recreate parts of the task if they were, for instance, asking for a label query. So the example here is the person asking, does it matter how I hold this, while also showing multiple ways of holding this. So it's multiple instance of the how to hold it feature, right? Secondly, we saw many instances of deictic gestures. As people were asking about things, they would point to them or hold them up to bring the attention to the object, and also some instances of iconic gestures. And this was, again, really nice inspiration for robots, because this allowed us to replace questions like, does orientation around X matter, which wouldn't mean anything to a normal person, or even a roboticist. If you don't know the conventions, you can't really answer this. With this kind of question, where you can just use your embodiment and do something to communicate what the feature you're talking about is. Right? So the study gave us insights into how people ask questions and inspired new ways for robots to ask questions. But next, we needed a framework in which the robot can actually learn something useful while also asking these questions to learn better, right? So a lot of the technical contributions in this work were basically implementing these different types of queries in one framework. And in fact, our implementation was also inspired by the ways people ask questions. So as I said, we saw people segment skills into steps. And we wanted to do, and the questions were about the specific steps, usually not about the global task. So we wanted to do the same for the task. But in the learning from demonstration literature, a skill demonstration is usually a continuous time series of the robot states, right? So there are existing methods for segmenting such time series, but we thought that automatic segmentation might yield segments that are not necessarily intuitive. So different people segment the same thing differently, right? So instead, we proposed a skill learning approach in which we take segmented skills from people. So people actually provide the segments themselves. So basically, instead of recording a continuous time series, the teacher only indicates a sparse ordered set of the states that the robot needs to go through in order to achieve the task. And this is actually a common technique to use in animation or in industrial robotics. Now, when you have multiple demonstrations of this type, you can model the skill as a sequence of keyframe distributions, right? So you can think of these as the sequence of constraints that need to be satisfied in a certain order. So in our implementation, we just use normal distributions on the 6th degree of freedom and effector of the robot, in some cases relative to a target. And so there is a mean and a covariance associated with each keyframe. And to execute, you just sample one from each of these distributions, and you just go through them in the order. So here are some examples of how this goes.
Okay.
Then go here.
Recorded.
Then go here.
Done.
Finish like this.
Here you go.
Yay!
That's it.
We started
Okay.
We started that with coffee beans, but after spilling a whole lot, we switched to the thing. So another nice thing about this was that it allowed the person to try things out as they are demonstrating. So the person, without having that pressure of being recorded all the time, they could just see, how would I do this? And then save when they're comfortable with it, when they have found the pose that they want the robot to be in.
Then go here.
All right.
Okay.
Finish.
So that basically addresses that problem I was pointing out earlier. Question? Yes, go ahead.
Did you tell them what language to use or what keywords?
Oh, okay. So the question is, did you tell them what language to use? Yes, so there was a fixed grammar of things that they could say, and we had it on a whiteboard next to the robot. We told them prior to the experiment that these are the commands, this is what they do. We trained them with that. All right, so now let's say the robot has learned this model from several demonstrations from the person, and now it's allowed to ask a question, like what should the objective of that question be, right? In this case, the objective is basically to increase the variance as much as it's allowed. So this corresponds to reducing to the minimal necessary constraints for the specific skill. Now, skills with high variance are desirable because they give the robot more alternatives of doing the same thing. For instance, if you're closing the box on the table rather than when you're holding it, there's an obstacle, but that variance lets you still be able to sample from the skill and do it. And this is actually a very primitive representation for skills, but it turned out to be quite powerful. So we could encode quite a number of skills with just this sequence of Gaussians. Now, so the goal is to increase the variance. And basically, the nice thing about this framework is that it allowed us to achieve this goal with all the different types of queries that we saw in people. So I won't have time to go into all of these, but I'll basically go through one of them to give an intuition and show some examples of the robot asking questions. So for labeled queries, basically, what we do is simply explore beyond what has been shown and play that, so try to execute something that has more variance, that goes outside the variance of what has been demonstrated in order to increase the variance, and just replay that and ask whether that's a valid way of doing the same thing, right? And there are some interesting questions, technical questions, regarding how you pick those points. So, for instance, how far should that point be varied? So you want to vary as far as possible so that if when that point is added to your distribution, it's going to increase the variance quite a bit. But the further away you go, the less likely it is that it was in the distribution that was intended by the person. So there is this trade-off, and what we basically did was try to write the utility of candidate points, and turned out in the way that we wrote it. So this was basically something proportional to the probability of the point being as part of the distribution that has been demonstrated so far, times the increase in the variance if the point was added to the cluster, right? And turns out we could just analytically solve this to specify points that are within a certain Mahalanobis distance. So basically, this was at first like a surprising thing, but it actually worked in practice. But of course, like we also needed to pick which point. So this only specifies one constraint on how you pick those queries. Basically, what we did for selecting the point, also while considering the kinematic constraints of the robot, was to sample a set of points that satisfy this constraint, and then pick the one that had the highest kinematic reachability for the robot. So here's an example of autonomously generated label queries based on 2 demonstrations.
Can I do this?
Yes, Simon, you can.
Can I do this?
No, Simon, you cannot. So here, when the answer is positive, the robot gets to use its own execution as a new demonstration of the same thing, and the person didn't spend very little effort to give that demonstration. But when the answer is negative, it was only wrong because of the very end. So the robot either has to throw the whole thing away, or it's going to learn to avoid something that's actually not wrong. So this is where this idea of partial label queries that we saw in people becomes really useful. So instead of getting a label for the whole execution, if you got labels separately, that would basically address this problem. Yes, Simon, you can.
Okay. Then I go here. Next I come here. Can I finish like this?
No, Simon, you cannot.
Thank you.
All right, and here I won't really go into how we generate the feature queries, but here are some examples of it.
I start here. Then I move here. At this point, does my hand have to be positioned like this?
Yes, Simon, it does.
At the start, does the position matter?
No, Simon, it does not.
At this point, does my hand have to be positioned like this?
No, Simon, it does not.
Can it be this?
No, Simon. So basically, the first 2 questions were where the answer that you get is very powerful. So you either learn that something is doesn't matter. So then with just one question, you learn that it can just have all the variance that it needs, which is something that you would normally learn from many varied demonstrations, right? In the second case, you learn that something has to be one value, so you better not ask any further questions, and you can be more conservative in when you're sampling for that. But the opposite, when you get the opposite answer, you learn that something matters or something doesn't have to be something. Then you can ask these follow-up questions, which was the last one. It learns that it doesn't have to be at that position, so the robot can ask these follow-ups saying, can it be this, can it be this, can it be this? It's basically making use of the context that has been set up to quickly get some more information from the person. All right, so after implementing these questions, basically we wanted to make sure that people can answer these questions, and also that they indeed provide the robot, they give some advantage to the robot as opposed to learning just passively from human demonstrations. So to make sure that the queries were indeed helping the robot, what we did is basically compare the robot learning purely from people's demonstrations without any questions versus giving the robot 2 demonstrations, which we take from the pool of the demonstrations that are given by people, and then for the rest, just answer the robot's questions. So have the robot ask questions and just answer. And we kept the total time spent teaching here constant because it's very difficult to compare these different types of queries by number. And ultimately, that's the thing. We want to be shorter. We just want to spend less time. And we did this for 2 very simple skills. And we measured success basically by two metrics. One, whether the robot had a way, so could come up with a way in a new scenario. So we would basically move the goal around to create new test scenarios. And also whether, if it had a way to do it, whether that succeeded. And we did the second only for a subset because it actually meant running many versions of a skill hundreds of times on the robot. So we did that for less. And not surprisingly, basically, we found that all queries resulted in queries that were more generalizable. So these were applicable in more scenarios. But also that all queries led to more successful skills. So what was happening in the passive cases was, as I mentioned earlier, people weren't showing enough variance. So in many test cases, the robot didn't even have a way to try to be able to sample from the distributions that was reachable. In other cases, it would try and also fail. But we did not see any big difference between the different types of queries and for these specific skills. And we also wanted to see that these different types of questions are intuitive for people, that they can be answered by people, and whether there's a preference for one or another. So again, we did another experiment where we compared these different types of questions, this time with novice teachers hearing the robot's questions. Is there a question?
Yeah, sorry to interrupt.
No problem.
Go on. I just wasn't sure I understood the last experiment. Were you controlling for how long the instructor, I mean, obviously answering questions takes time, and during that time, one could provide extra demonstrations. How many demonstrations were you giving, and were you controlling for time?
Okay, so the question is, were you controlling for time? Yes, so there was a constant session time. In one case, the person would just give demonstrations until time is up. In the other case, we first took 2 demonstrations from these people and calculated how much time it took for them to give these, and then generated questions. So have the robot generate questions based on these demonstrations, and we answered the robot's questions.
Thanks. And so roughly how many demonstrations?
I see. So it varied a lot across people. It was somewhere from 6, people had challenges, to like 20. Yeah. So coming back to this newer experiment. So here we had, the thing we kept constant was the number of demonstrations. So people would show a certain skill 2 times. These were similar skills, again, goal-directed. People would show 2 demonstrations, and then the robot would ask 2 questions. And we told people only that the robot might ask questions and that they can answer it in however they want. And here we kept the questions constant, so it wasn't based on what they had shown, so that we made sure that everybody saw the same questions. All right. And here the main finding was that people had no problem basically answering all the different types of questions, but we saw some preferences for one or another, so some arguments for using one or the other. For instance, feature queries were seen as being the smartest questions, and people thought that these questions indicated a higher level of understanding of the task from the robot's part, and also pointed out that it didn't require that the task be repeated either by the person or the robot. So that was something they had noticed. Why is it important for queries to be seen as smart? The reason that we cared was that in a different study, we had seen that people are less likely to comply with the robot's questions, to answer it, if they think that it doesn't make sense to have that question, to ask that question based on what they had shown. But in other cases, you might want the robot not to set very high expectations by asking this smart question and have the user expect that it's very intelligent. Secondly, the survey suggested that label queries were easiest to answer from a human perspective, but this was not very significant. But we saw that it was supported by the time that people spent on answering the question. So here I'm showing the average duration of what the question takes and what the answer takes. And here, label and feature queries were both yes-no questions. But we saw that label queries took less time for people to answer, supporting that it was easier to answer. So what was happening in the feature queries was basically people were thinking more before answering. So we started seeing signs of hesitation on what the answer should be. So here's an example of that.
Can I forward different heights?
Yes.
So basically, the person is not sure what it means for the robot if it knew that it can pour at different heights, right? So this points to potential difficulties in getting the right answers from people for feature queries. We basically demonstrated that the robot greatly benefits from being able to ask human-like questions, and that these questions were in general intuitive for people. What I'd like to do now is very briefly talk about some of the related problems that I've worked on, which basically tie also to this problem of enabling people, addressing issues that people have when they're trying to teach a robot. So the skills that I've talked about so far were all object-directed skills. So these involved the robot interacting with the environment. But robots that operate in environments where there are humans will need to have a whole set of skills that involve direct interaction with people. And programming such skills, having users program such skills, have their own very unique challenges. For instance, the person being the programmer also wants to be the person who is interacting with the robot. And the ability for users to be able to program these kinds of skills is particularly important because they're the ones who will be interacting, and it's important that it's done their preferred way. So basically, the work that I've done in this space was focused on this interaction of human-robot handovers. And the thing that we saw was that if this was not even people interacting with what they taught, if someone taught the robot as opposed to the robot planning based on the person's kinematics, that was preferred by a third person as a way of presenting an object. And secondly, the types of queries that I talked today were focused on skill learning. So these were where the robot was learning how to do something. Now, a complementary problem to the skill learning is learning what the particular goal is for a given task, assuming that the robot has the basic skills to accomplish that goal once it has learned it. So maybe it involves pick up and place, and the robot can do it. So we looked at such task learning problem in several domains, some more toy domains. But basically, we found that similar challenges of people not demonstrating variance, people having flawed mental models, also existed in these kinds of even simple learning problems. So again, having the robot ask questions in these problems made a lot of sense. And again, this involved different types of questions that part of our human study was actually involving these types of task learning things, where it wasn't about how you moved, it was about what the goal was. And again, there was a role of embodiment in supporting the interaction. Things like pointing to things or looking at things, and even in some cases, being able to manipulate the environment to ask a question. Now, besides having the robot ask questions, an alternative complementary method that I explored in my thesis was what I call teaching heuristics. These are instructions that we give to the user about how to teach. And the intuition for this is really simple. It's basically people might not naturally be optimal teachers for machine learners, but they're intelligent and flexible. So if we told them, you should do this, you should show more variance, there's a good chance we can just influence them to do the right thing for the system. And the way that we tried to do this systematically was by studying the teaching problem. So there is actually a whole field of theory that studies teaching problems, just like learning problems. And a lot of the challenges are finding optimal teachers that are efficient. So the teaching problem is an NP-hard problem, and it's you need to somehow exploit the structure of the problem in order to have efficient teaching algorithms. So what we try to do is also devise teaching algorithms and look at how people are differing from these optimal teachers and try to explain to them what they need to do to be an optimal teacher. And basically, we demonstrated across a variety of domains, so this wasn't necessarily just focused on robotics, but at the end we tried to get to robotics. We demonstrated that having these instructions across all domains made a significant difference in the quality of the input that you could get from the person. And in my more recent work at Willow Garage, I tried to look at this idea of instructing users in a more general sense. So in most of my HRI studies, not providing good learning examples is not the only problem. So there are many breakdowns until I get to the point where the person can even demonstrate. So we have to put these whiteboards, as you were asking. So there are things that we need to instruct people about before they can even start interacting with the robot to provide data. Now, in my experiments, I am there to train them and to have them exercise and not break the robot. But when people buy robots, I'm not going to be there to help them with that. So basically, the challenge for this study that I worked on, which you saw videos earlier, was that we would bring people into the lab and not tell them anything about how the system works and leave them alone with the robot. And then try to do things to support this interaction so that they could successfully train the robot to do something. And here are some examples of the different types of challenges we needed to address. So one is when people find a way to do what they want, and then they'll stick to it, even though it's not the most efficient way of doing it. So I call this superstition. So once they have found a way that works, they don't go out of that comfort zone, even though they're spending much more time than they're supposed to. An example of this was this person who would freeze the robot's arm every time before saving a pose, whereas he really didn't need to. So he could just move there and save the pose. So here he's go.
Left arm holding.
Save pose.
Pose saved.
Release left arm.
Left arm released.
So he has to go through 3 commands as opposed to 1 command. And when this is over the whole task, it's like 3 times more time spent on this. The second one was, and you could also consider the first one as being functional ignorance, was not knowing that there's a certain functionality that you can use and being stuck because of that. So the example that's here is that the person accidentally deletes everything she has saved, and she freaks out, and she has to go from scratch, whereas she could have actually said undo.
Save pose.
All poses deleted. Skill cleared.
No, that's not what I said.
Yeah, so basically what we tried to do in this work was to design the interface in a way that tries to avoid these problems, but also started looking into designing instructional materials like the user manuals that we would give people, tutorials that could be even administered by the robot, or instructional videos. And it turned out that video, seeing people do the same thing first, really was the most powerful. Some people didn't even know that they could touch the robot, so that was the first challenge that they were faced. Okay, so for the last 10 minutes or so, I'd like to tell you more about my plans going forward and what I'm currently basically working on at Willow Garage. So the bigger cause that I'd like to contribute is to make personal robotics a reality. So I'm actually personally invested. So when I'm older, I want to have a robot at home. And some people are not very optimistic about this, but I think it's not as far. I think that the technology is getting there. So this is an example from 2008. So this was, it wasn't even it was PR1, it was not even the polished version. And physically, we could already do a lot of useful things by, yes. By having a person joystick the robot. So I think that the technology, hardware-wise, is really getting there. And I think the price points will catch up. very fast. But there are many unknowns about how people will interact with these systems and what it will take to get these systems integrated into our daily lives. And this is where I'd love to make some impact. So the more specific goal that I've set for myself is to lead the first long-term deployment of general-purpose service robots. And there are two reasons that I wanted to focus on service robotics. Remember that the three strategic domains emphasized by the NRI, we actually already have end-user programmable commercial systems available today for these other two domains. And I actually think that programmability and usability has been a key factor in the success of these systems getting out there. So these robots have actually been advertised. So the Baxter robot, you might have seen this, is advertised as being a robot that can be taught by a non-technical hourly worker. Similarly, this seemingly very different system that I hadn't heard for a long time is advertised as being easy to train by just walking it through the task that it needs to do, and just then saying go to work. So I think this is very exciting, and I think the long-term deployment of these systems is already happening. But the service robotics is actually where there are a lot of challenges and opportunities for making this happen. And the second reason I'm interested in service robotics, particularly domestic robotics, is that homes and domestic users are greatly varied. So every home has their own features, and home is the one place people get to express their preferences. So this basically gives a lot of value proposition for having a robot that can be programmable. And my strategy is basically, these are some of the things that I want to keep in mind, is that first of all, trying to target early adopters. So projects that we see currently are targeted towards the users who would benefit from having these most. So older adults or people with disabilities, if they had this robot, they could really benefit from it. But I think what I'd like to do is address an early adopter population who would be okay with not making profit from having this robot. And the argument for this is that if we cannot do it with these users who would be forgiving of errors, etc., it's very hard to do it with the rest of the population. Once we achieve this, it doesn't mean that now grandma can use the system, but I think this will let us take care of some of the early challenges that we're still not being able to do, and will pave the way for mass adoption. And secondly, I think that we need to be more realistic about limitations of robots. I think the scenarios that we're setting for ourselves are too challenging. The fact that a robot cannot do a task from start to end completely autonomously doesn't mean that it cannot be useful. So I think we need to find the right compromise between sharing tasks between humans and robots. And thirdly, I'd like to focus more on what is needed rather than what is challenging. I think there's a lot of work in programming by demonstration or learning from demonstration literature that's very challenging, dynamic tasks like playing ping pong or like balancing a pole. I find that very hard. But I think solutions to tasks in the household might be much easier and more achievable in a robust way. But I think long-term deployments are still some years away. So what I'm currently working is, as a postdoc, is developing the tools that will enable or facilitate this goal. So the way that I've been working for this since last summer's challenge is basically setting challenges for myself. So these are the 3 challenges that I'm working on. I haven't made too much progress yet. So one thing that has been bothering me about, again, the learning from demonstration literature is that these systems are presented to be very generic. So it's a learning system. It can just learn anything. But we never see them evaluated on more than 5, the most I've seen 8 different skills. And the problem is not that there isn't enough space in the paper. It's that I think if we had these large lists of skills, I bet that every individual system will hit a certain wall and will require the designer of the system to go back and change things. So possibly add new features or change the representations. So the first challenge is basically to try to build a system that works for 100 or some arbitrarily large number of skills. And the point of this exercise is to exactly go through that process to try to find more systematic ways of building scalable systems. And in addition to the benefits of benchmarking that we have seen in other fields, this will also allow understanding the common structure of tasks for a certain domain. And in my case, I'm interested in domestic robotics. So what I've been doing is trying to look into sources for benchmark tasks that would be useful tasks for robots. And one interesting result from looking at user-generated chore lists was that there are some structures that could be exploited. So one finding is that a lot of, maybe half of the tasks that are in this chore list are what we considered as cleaning tasks, which could be described as applying a tool on a surface. So usually the verb describing the task is the tool itself. So things like wiping, vacuuming, scrubbing, what else, dusting. These are all involve a surface and a tool being applied on the surface. And most of the time, this surface, 95% of the time, this surface was a fixed thing in the house. So basically, the idea here is that instead of trying to learn these tasks at the level of how do I move my end effectors and grippers, trying to have explicit representation of these task structures and having the robot try to fill in the gaps given this blueprint of what the task consists of. And I think this has been the key in the success of these systems. They have tasks that have a very specific blueprint, and all the user does is fill in the blanks for these. Now, another important challenge is to allow programming robot skills with a single demonstration. This has been also another problem that people have been working on. And this is motivated by lessons learned during my thesis work that people just don't like to repeat something twice. And turns out you can already do pretty well by exactly mimicking a single demonstration. So this was me programming the PR2 to do a t-shirt fold. And the robot just goes exactly through the motions that I did, and it can successfully do it. And even when you start adding explicit representations of what's in the environment, in this case, what are the objects on the table, you can still learn quite a bit from a good single demonstration. So here's an example where the robot automatically encodes relativeness of the robot's poses to objects in the environment, simply by always considering the nearest object as being the coordinate frame for the saved poses. And then when the objects move around, this still works. Now, one of the key problems that I've been working here is to allow the user to quickly insert meta information in addition to the demonstration to do things like fixing the demonstration so that it works in a different scenario. There was another example where you can correct the assigned coordinate frames, maybe if it was wrong, or even maybe look at what the robot is seeing and removing things from the robot's world model so that it doesn't pay attention to those things like that. And I think that we should have multiple versions of these tools to have more and more complex, to accommodate more and more complex skills until we can cover a large set of useful skills. So on one end, the challenge is basically what I worked on, was having a novice come in for the first time and be able to do things with the robot, figure out them very quickly. But on the other end, we want more advanced tools, things like Photoshop, which still doesn't require writing code at the level that we do, but requires time to master. And I think at that end, we can start thinking about more complex programming constructs like parameters or loops or if-then conditions, etc. And I think at that extreme, the challenge is to make sure that people other than myself or whoever is developing this be able to learn this tool and get as good as the designer with a decent learning curve. And I think that this is basically where some of the first long-term studies that I will do will happen. So to wrap up, basically what I tried to do today was to motivate the vision of end-user programmable robots. And I overview some of the work from my dissertation that demonstrates challenges that people have in dealing with these systems, and some of the solutions that we developed focusing on having the robot ask questions, and some of other related problems, and I try to outline some of the steps that I want to take towards this vision. Here are some references. Some of these are not published yet, but I'd be happy to share preprints if you're interested. And thanks again for inviting me, and thank you for your attention.